Up until now, we've talked about unsigned binary numbers, where unsigned means positive numbers. And so now we're going to talk about signed binary numbers, and signed binary numbers can represent both positive and negative numbers. So signed binary numbers means we can represent both positive and negative numbers, whereas unsigned binary numbers, which we've been talking about so far, represent only positive numbers, where 0 is we're considering as positive. So there are two types of signed binary numbers: signed magnitude numbers and 2's complement numbers. And mostly in this class we're going to deal with 2's complement numbers, but we'll look at both of these types of signed binary numbers. So signed magnitude numbers have one sign bit and n-1 magnitude bits. The sign bit is the most significant or leftmost bit, and this is really kind of how we think about it. So ignore this for now and think about, let's say we have some number 5. We want to say plus 5. So then we would take the most significant bit and represent the plus. We use 0 to represent a plus or positive number, and then the rest of the bits indicate the magnitude. So we have a sign bit, and then we have magnitude bits. And so in this case, we'd have, if we had a 4-bit signed magnitude number, would represent plus 5 as 0, 1, 0, 1. Now if we wanted to represent minus 5 or negative 5, we would have, well, the sign bit now is negative, and we're going to use a 1 to represent a negative value. So our sign bit in this case would be 1. And then our magnitude bits would be the same, 1, 0, 1. So now try writing the 4-bit signed magnitude representation of positive and negative 6. So pause the video and try that, and then we'll work it out together. So plus 6 is, well, we have a 0 to indicate positive in the sign bit, and then our magnitude bits are 1, 1, 0 to represent 6. So we have our sign bit and our magnitude bits. And minus 6 is, well, and then we have a 1, a negative, to indicate negative in our sign bit, and our magnitude bits are still the same, 1, 1, 0, to indicate 6. So what is the range of an n-bit signed magnitude number? Well, let's start with an example. Let's start with 4-bit signed magnitude number. What's the most, or the smallest or most negative number that we can represent? Well, the most negative number is, well, we would have a 1 in the sign bit to indicate negative, and then all 1s in our magnitude bits. So we'd get negative, the magnitude is 1, 1 plus 2 plus 4, so we get minus 7. The most positive number is, well, a 0 in the sign bit to indicate positive, and all 1s in the magnitude bits. And so we get minus 7 to 7. Okay, well, we could try another example. We could try a 4-bit signed magnitude number. Well, 4-bit signed magnitude number would be 1. The most negative number would be 1 in the sign bit, and then all 1s. So that would be minus 15. And then the most positive would be a 0 in the sign bit, and all 1s. So it'd be plus 15. So we see a pattern here. Well, with our 4-bit signed magnitude number, the most negative number is 2 to the, well, not 4, but it's 3. It's close to minus 2 to the 3, but it's actually 2 to the 3 minus 1, and then we put a negative sign on that. And the most positive number is 2 to the 3 minus 1. Okay, well, that was for our 4-bit signed magnitude. What about for 5-bit? Well, for 5-bit, the range was 2 to the 4 minus 1, negative sign on that, 2 to the 4 minus 1. Okay. So we see a pattern here. It's actually, if we write it in terms of n, 2 to the n minus 1, minus 1. That's the negative, most negative number you can represent, and the most positive number is 2 to the n minus 1, minus 1. And so for our example of 4 bits, we'd have minus 2 to the 3, or 4 minus 1, which is 3, minus 1. So we get our minus 7 to plus 7. And the number of values we can represent, well, let's do it for our 4-bit value, our 4-bit sign magnitude number. Well, the negative numbers we can represent is minus 1 to minus 7. So that's 7 in the negative range. And the positive range we can represent 0 and 1 to 7. Okay, well there's 7 here, so 0 and then 1 to 7. So that's 7 values. This is 1 value, and that's 7 values in the negative range. So we can represent 7 plus 1, 8, plus 7, 15 values. So what happened here? We have a 4-bit value, but we can only represent 15 unique values, right? Minus 1 to minus 7, 7 values. 0, that's 1 value. And 1 to 7, that's 7 values. So 7 plus 1 plus 7 is only 15. Somehow we lost an encoding, right? We should, with 4 bits, we should be able to represent 16 unique values. Well, we lost one of the values by redundancy. So 0 can be represented as positive 0 or negative 0. And so we have some redundancy. We lost one of our encodings to redundancy. And another problem is addition doesn't work. So let's take, for example, minus 6, that number we just represented, plus a positive 6. We add that together, 0 plus 0, 1 plus 1, we get 0, carry the 1. 1 plus 1 plus 1, we get 3, which is 1, carry the 1. 1 plus 1 plus 0 is 2, which is 0, carry the 1. Ugh, that's just wrong, right? We would ignore that carry out still. But 4-bit addition, 4-bit result, we had 4-bit operands. Here's our result. Minus 6 plus 6, and we got 4? Wrong. It just doesn't work. And that issue we pointed out, we have 2 representations of 0, plus and minus 0. So this redundancy is never, is never a good idea for circuits, because now we have to deal with that redundancy. Our circuits have to interpret 1, 0, 0, 0 as 0 as well as all zeros. So our circuits would have to detect both of those values as meaning 0. So let's fix this. And the way we're going to fix both of those issues is by using another representation called the 2's complement representation. So this representation does not have the same problem. Addition works, and we have just one representation of 0. So 2's complement numbers, the most significant bit has the weight of minus 2 to the n minus 1. So if we have some number here, let's say we have a 4-bit number, this would have the weight of 2 to the 0, 2 to the 1, 2 to the 2, and instead of the most significant bit having the weight of 2 to the 3, it would have the weight of minus 2 to the 3. So the most significant bit has the weight of negative 2 to the n minus 1. So negative 2 to the 4 minus 1 in this case, or minus 2 to the 3 to the 3rd power. And so if we wanted to see what the most positive 4-bit number is, well, we wouldn't want to put a 1 in that place, because that would make it negative. So the most positive 4-bit number is 0, 1, 1, 1. So we'd put a 0 in that negative weighted place, and then we want to fill up all the positive weights with 1s. And so the most positive number is 7, or 1 plus 2 plus 4. Most negative 4-bit number is, well, we'd want to put 1 in that most significant bit. Right, we'd want to put a 1 here to get a negative value, and then we don't want to add any positive values. Right, we want to put zeros here because we want to get the most negative number. If we put a 1 there, for example, instead of being -8, it would be -7. It would be -8 plus 1. Okay, so the most negative number is, in this case, in the 4-bit case, -8. And we'll notice that most significant bit still indicates the sign. So we can kind of use that most significant bit as the sign bit. Right? So if we have a 1 in that place, we know it's negative, because even if we filled up the other bits, the other binary digits, with 1s, then we'd get, well, -8 plus 1 plus 2 plus 4. So -8 plus 7 is -1. So that most significant bit still indicates the sign. So what's the range of an n-bit 2's complement number? Well, we found that the range of a 4-bit 2's complement number is, well, -8 was the most negative number we could represent, and +7 was the most positive. And so we can see that this is -2 to the 3, and this is 2 to the 3, or 8 minus 1. And so for 4-bit numbers, that's the range. So we could write that in terms of n, -2 to the n minus 1, to 2 to the n minus 1, minus 1. And so generically, for any n bits, 2's complement number, here's our range. And how many values can we represent? Well, let's take again this example. Well, we have 0 in the positive range and 1 to 7. So we have 8 unique values. And here we have -1 to -8. And so in the negative range, we have 8 values. So the total number of values we can represent is 8 plus 8 is 16. So we have, again, with our 4-bit value, we got our entire number of values that we can represent with 4-bit values. And so we can represent our 16 unique values with n. Well, right, where this was with 4 bits, we can represent a total number of 16 unique values. So with n bits, we can represent, or in other words, 2 to the 4 unique values. And with n bits, we can represent, well, 2 to the n values. So let's talk about this method of taking the 2's complement. So I want you to replace this taking the 2's complement with flipping the sign. So let's call this the flipping the sign method instead of taking the 2's complement. So flipping the sign method just makes a positive 2's complement number negative, or a negative 2's complement number positive. So it changes a number from either positive to negative or negative to positive. It just flips the sign. Keeps the magnitude the same, but it just flips the sign. And the method is to invert the bits and add 1. So we're replacing this term, taking the 2's complement, with the flipping the sign method. So let's say we want to flip the sign of this 2's complement number, 0, 0, 1, 1. So we know that that is 1 plus 2 is 3. And so we're going to invert the bits. So let's do that. Invert the bits. 1, 1, 0, 0. Just means to change. Inverting means to change the 1 to a 0 to a 1. So we're going to invert those bits. And then second step is to add 1. Then we add 1. So we're going to get 1, 0, 1, 1. And so this, we've started with the 2's complement representation of 3. So now we flip the sign and we get the 2's complement representation of -3. So we flipped it from positive to negative. And we can use that same flipping the sign method to flip the sign from -3 to +3. So let's do the same method on -3 to flip the sign to +3. So we start with, here's our 2's complement representation of -3. Step 1, we invert the bits. So we get 0, 0, 1, 0. And this is called the 1's complement of the number above it. This is called the 1's complement, just so you know. And now step 2 is we're going to add 1. And so we started with -3, now we're adding 1. We get 1, 1, 0, 0. And now we started with -3, and now we flip the sign to get +3. And so this is called the flipping the sign method. We're going to replace this term with flipping the sign method. And so we can take a negative 2's complement number, use this method to flip the sign and turn it into a positive 2's complement number with the same magnitude. Or we can take a positive 2's complement number, use this method to flip the sign and keep the magnitude the same and turn it into a negative 2's complement number of the same magnitude. So let's do an example. Pause your video right now and take the 2's complement, or in other words, flip the sign of this 2's complement representation of the number 6. Okay, so we're going to do this together now. We're going to invert the bits, or in other words, take the 1's complement. So, right, we invert those bits. 1, 0, 0, 1. Step 1. Step 2 is to add 1. 1 plus 1 is 0. Carry the 1. 1, 0, 1. And so here we started with +6, and we took the 2's complement, or flipped the sign, and now we have the 2's complement representation of -6. And we can double check that. So we have the 1's place, the 2's place, the 4's place, and the -8's place. So we have a -8 plus a 2 gives us -6. So this is also useful, so this flipping the sign method is also useful to find the decimal value of a 2's complement number. So we have 1, 0, 0, 1 base 2. We know it's a negative number because it has a 1 in that most significant bit, but we don't know what the value is. So we know this is some negative something. I'm not sure what the something is. And so we can take the 2's complement or flip the sign. So invert the bits, 0, 1, 1, 0, and add 1, step 2, is to add 1, and we get 7. So we know the magnitude, we just changed it from a negative number to a positive number. So we know the magnitude is 7, and so now we can fill that in. So 1, 0, 0, 1 is the 2's complement representation of -7. So this flipping the sign method, or taking the 2's complement method, is useful for dealing with negative 2's complement numbers. Remember to replace this term, take the 2's complement, with flip the sign. So now let's talk about 2's complement addition, so adding 2's complement numbers. So we have these 2's complement numbers. We know this is a positive number This is a negative number. And we can figure, well, the top one we can figure out is 6. We could flip the sign on that bottom one to figure out what the magnitude is. 0, 1, 0, 1. Invert the bits. That's step 1. Step 2 is add 1. And so we get 1 plus 1 is 0, carry the 1. And so we're adding 6 and minus 6. I didn't already tell you that in the title. And so we're expecting to get 0. So let's see what we get. So 0 plus 0, 0, 1 plus 1, 0, or 2, carry the 1. So 1 plus 1 is 2, which is 0, carry the 1. 1 plus 0 is 2. In other words, 0, carry the 1. 1 plus 0 plus 1, again 2, which is 0, carry the 1. So let's see, did we get 0? 6 plus minus 6 should be 0. Did we get 0 here? Well, we have to remember, if we have 4-bit operands, we get 4-bit results. So this is the result. This is one of the most common errors here, is to include that 5th bit in the result, but it should not be included. So in fact, we did get 0. We added plus 6 and minus 6 and got 0 as expected. Remember, 4-bit addition, 4-bit result. 10-bit addition, 10-bit result. Whatever bit width the operands are, that should be the result for addition. And so what's going on here? What's this 1? Is that overflow? No. In 2's complement addition, that does not indicate overflow. It's just a carry out of the most significant bit. This bit does not indicate overflow for 2's complement addition. It does for unsigned binary addition, which is what we started with in this chapter. But for 2's complement addition, that carry out of the most significant bit does not indicate overflow. Okay, so let's do another example of 2's complement addition. So try this addition on your own, pause the video, and then we'll work it out together. Okay, so we have 0 plus 1 is going to give us a 1. 1 plus 1 is 2, which is 0. Carry the 1. We have 1 plus 1 plus 0 is again 2. 0, carry the 1. 1 plus 1 plus 0, 2 again, which is 0, carry the 1. And so what value do we get? Remember, 4-bit addition, 4-bit result. So here's our result. Our result is 1. And we added these values. This was our -2, and this is 3. Minus 2 plus 3, we expect to get 1. Check, we got it. Absolutely ignore the carry out of the most significant bit. It means nothing in 2's complement addition. And we could have also written these as hex values. So we could have written this as hex for shorthand for binary. Hex E plus hex 3. But when actually doing the addition, we want to use binary. So remember, for 2's complement addition, the carry out of the most significant bit means absolutely nothing. So we just ignore it. And remember, 4-bit addition, 4-bit results. If we had had 8-bit addition, we would have had an 8-bit result, not a 9-bit result. And so these work out as we expected. -2 plus 3 is 1, and 6 plus -6 is 0. Now we can use the 2's complement representation of numbers to perform subtraction as well. So to subtract a 2's complement number, we're going to flip the sign and add. And remember, we flip the sign by using the flipping the sign method, or the taking the 2's complement method. Remember, we're replacing that term with the flipping the sign method. So here we have 3 minus 5 is what we want to perform. We can do that by using 3 plus a negative 5. How do we get negative 5? Well, we start with plus 5 and we flip the sign or take the 2's complement to get negative 5. So step 1, invert the bits. In other words, take the 1's complement. So step 1 is invert the bits, and step 2 is add 1. So we get 1, 1, 0, 1. And so we get 3 plus a minus 5, and we add them together. 1 plus 1 is 0, or is 2. 0 carry the 1. 1 plus 1 is 3, which is 1 carry the 1. We get a 1 here, and 0 plus 1. So we get 3 minus 5 is minus 2, as we expect. How do we know it's minus 2? Well, we can take the 2's complement or flip the sign of that, 0, 0, 0, 1, invert the bits, and second step is add 1. 1 plus 1 is 2, 0 carry the 1, 1 plus 0 is 1, and so we get the magnitude was 2, and we know it was a negative number. And so it all checks out. 3 plus minus 5 is equal to minus 2. So we actually perform subtraction by performing addition of the negative number of so 3 plus minus 5. We flip the sign of plus 5 and add it to 3. So let's compare the number systems that we've talked about so far. So we've talked about unsigned binary numbers, which have a range of 0 to 2 to the n minus 1. So for 4-bit, for example, we have 0 to 15, 0 to 2 to the n or 2 to the 4, 16 minus 1, 0 to 15. And the number of values we can represent is, well, 0 plus 1 to 15, or 16 values. Generically, 2 to the n values. For sign magnitude numbers, we can represent this range of numbers. For 4-bit, it's going to be 7 to minus 7. And remember, we lost one of our values here by redundancy, so we can't represent 2 to the n values. We can only represent 2 to the n minus 1 values. And then 2's complement goes from a range of plus 7 to minus 8. And so we use these, basically the plus range up to 7 is the same as unsigned, and then we take these values and use them to represent negative numbers. And so the number of values we can represent, we can use all of our values again, is 2 to the n for 2's complement and unsigned binary. Only signed magnitude numbers, we lose one of those values we can represent because of redundancy, the redundant representation of 0.